Hello, and welcome to the video presentation for Project 23056, the Smart Medical Drainage Catheter, sponsored by Becton Dickinson, or BD.
Hi, I'm Hasina Shear, and I'm team lead.
Hi, I'm Karis Brackpool, and I'm the information lead.
Hi, I'm Cynthia G., the assistant team lead.
Hi, I'm Bianca Rodriguez, and I am the procurement lead.
Hi, my name is Catherine Hong, and I am the electrical lead.
Hello, I'm Muhammad Delta, and I'm going to be the mechanical lead.
Per our project description, the purpose of this project is to develop a functioning prototype of a smart medical drainage catheter that is able to be implanted and will remove and collect the excess fluid from bodily cavity to be collected and disposed of safely. In addition to this, the prototype will automatically measure, record, and preferably wirelessly communicate parameters during the process of fluid inline removal. The parameters that will be evaluated through this are the total quantity of fluid drained over time and duration of drainage procedures, detection of clogs, and the standard biometric measurements of fluid, including pH and temperature.
Approximately 2 million people in the U.S. will develop excess fluid known as pleural effusions or ascites due to underlying terminal conditions. This excess fluid pushes on the internal organs, making it difficult to breathe, eat, walk around, or conduct other normal daily activities. BD currently offers either an indwelling pleural or peritoneal catheter to be implanted for the patient to collect and dispose of the excess fluid using bottles or bags.
With the current setup, patients must use bottles to collect and dispose of waste 3 to 7 times a week, all while noting how long the drainage session was and the volume of liquid drained. When the user is not draining, the drainage segment that includes the bottle is removed and the user will tape down the external portion of the catheter.
The medical need our project aims to address is to ease the patient's process of drainage and provide clinicians with numerical data.
Our goal is to develop a smart medical catheter that detects clogs and notes the volume of liquid drained, the duration of the drainage process, pH, and temperature, while also keeping the process simple and lightweight for the patient so as not to add any excess work to the current process.
Our approach to the problem took the following format. Each team member took on a required metric and researched the best fit sensor for our system that would record that measurement. We then determined the placement of where we would attach each sensor and the order in which they would go. Next, we individually verified each sensor to ensure proper function while providing accurate data for each element of the system we wanted to measure. Once we determined each sensor was operating properly, we integrated all sensors into the existing catheter system to run simultaneously.
We will now cover the major system requirements that drove our design.
In terms of interface, our approach to the data save and display requirement is utilizing a Raspberry Pi and/or computer to save and display a CSV file of the data.
For the patient usability requirement, we wanted to make sure that the user can interact with the interface with relative ease. So our approach was to have the sensors automatically start when the drainage session begins and stop once it is finished. For our accuracy requirement, we wanted to ensure that the sensors could measure the values in the predetermined normal range for their metric, as well as outside the range to indicate an abnormality. Our next requirement was to ensure that we maintained the original function of the drainage catheter. Once the sensor system was integrated, we simulated the drainage process by developing a fluid storage system to mimic the body cavity.
Next, we will go over our design concept. You can see the existing BD drainage catheter bottle system to which we attached our sensors. At the top of the model, you will see the Sensorion flow sensor that measures the flow rate to give us volume and the duration, and it also measures the temperature. Below the sensor is the ISFET that will measure pH using 2 different probes. Lastly, we have the pressure sensor that uses pressure change to detect a clog that has occurred.
Next, we have our requirement verifications for each metric selected, which was volume drained, duration of drainage, temperature, clog detection which used pressure, and the pH using ISFET.
The Sensorion liquid flow sensor measures flow rate and temperature of the pleural fluid drainage. Thus, our process in testing was placing the sensor in line with the tubing and running the software on the Raspberry Pi. The terminal successfully outputs the flow rate and temperature, therefore giving us the measurements to further calculate volume drained and flow duration. The Adafruit MPR-LS ported pressure sensor measures the pressure of the tubing, thus detecting whether there is a clog within the tubing. The sensor is connected to the Raspberry Pi and is attached to tubing that is in line with the BD vacuum bottle. For testing clog detection, the software notes when the fluid pressure is below a certain PSI.
Here, we are demonstrating our simulation of a clog by pinching the tubing to signal a drop in pressure. When the clog was demonstrated by pinching the tubing, we can see in the output code here that when the pressure is shown in the left column to drop below 8 psi, then the system outputted a clog detected message. Prior to the clog, the system will output a no clog detected message, which we can see change here when the pressure drops from 11 to 4 psi.
Is an ion-sensitive fuel effect transistor that measures the ion concentration in a solution. Thus, we are able to measure the pH level within the pleural fluid. The sensor follows a serial communication protocol and is directly connected to the Raspberry Pi through USB.
While we do not have a complete system running cohesively yet, the team has managed to find sensors for all the parameters and items the sponsor required. Due to software coding issues with our vendor, we are unable to have ISPA working as of now, but are working diligently to solve this problem. The team has managed to take a drainage catheter that had no patient data output. One of the biggest problems faced by our team for this project was redefining the project scope by reframing the parameters and narrowing down the requirements to make them achievable. In addition, we went through many design iterations that we believed would work, but then failed due to various reasons, setting us back in our prototyping phase. However, the team learned a great deal from this project and are very proud of how we persevere in times of uncertainty. For our safety, environment, and other considerations, the team researched and found all of these standards relevant to the project. For example, ISO 13485 is a widely used standard for the design of medical devices. We did not have to comply with most patient interface standards, as all of our sensors are external to the body, and for data protection rights, the patient themselves will be receiving the data instead of the practitioner.
Our deliverables to our sponsor will be the sensor system and the code created with it to obtain the desired metrics. This includes the flow sensor, which provided volume, duration, and temperature, the pressure sensor used for clog detection, and the ISFET for pH. We will also provide a user manual, the software design documents, and the software design. Our deliverables will be completed by May 2nd, 2023, and will be delivered to our sponsors Becton Dickinson in Tempe, Arizona.
Finally, the team would like to acknowledge our mentor, Don McDonald, as well as all of our sponsors at BD, Christine, Peter, Chad, and Akiva.